So, we just got some huge updates about 3I Atlas as the Hubble Space Telescope captured new images in December. For the first time, we can watch jets from another star system wobble back and forth and calculate exactly how fast the object is rotating. In this presentation, I will break down what these new Hubble images actually reveal, why this switching pattern is so important, and what this tells us about objects traveling between the stars. Let's first talk about what Hubble actually saw on December 12th and December 27th. The telescope captured two distinct jets. One jet points toward the Sun and the other jet points away from it. But here's what blew everyone's minds. On December 12th, one of these jets was bright and the other one was dim. Then, 2 weeks later, Hubble took another picture on December 27th and the brightness had completely flipped. The jet that was bright on December 12th was now dim, and the jet that was dim on December 12th was now bright. They switched places. This is not random. This is a clean, organized pattern. The jets are taking turns being bright. When one brightens up, the other one fades down. They follow an opposite pattern from each other, and scientists needed both images 2 weeks apart to see this switching happen. That is what proved the object is spinning. So why are the jets switching brightness like this? Well, the answer is actually pretty simple. Rotation. Think about a lighthouse. The lighthouse has a bright beam of light that spins around in a circle. When the beam points toward you, it looks super bright. When it points away, it looks dim. The light itself isn't changing. Your viewing angle is changing because the lighthouse is rotating. 3I Atlas works the same way. The object has two jets shooting out from opposite sides. As the whole object rotates, those jets tilt toward Earth and then away from Earth. When one jet tilts toward us, it looks brighter. When it tilts away, it looks dimmer. The switching pattern we see in the December images is direct visual proof that 3I Atlas is spinning. The jets themselves are not turning on and off. We are just seeing them from different angles. This is massive because until these December images, nobody had ever directly measured the rotation of any object from another star system by watching its jets wobble. Now that we know it is spinning, scientists can use this switching pattern to calculate exactly how fast. A team of astronomers spent 37 nights watching 3I Atlas through telescopes in the Canary Islands. Night after night, they measured how the jets changed angle as the object rotated. What they found is that the jets complete one full wobble cycle every 7.7 hours. Wobble means the jets trace a cone shape as the object spins, making them appear to swing back and forth from our viewing angle. But here's the key. The wobble takes half as long as the full rotation. Think about it like this. If you watch the North Pole of Earth, it traces a circle every 24 hours, but Earth only spins once every 24 hours. The pole just looks like it wobbles twice as fast because of the geometry. Since the wobble period is 7.7 hours, the full rotation period is twice that, 15.5 hours. This matches perfectly with something else scientists measured back in July when 3I Atlas was pulsing in brightness every 16 hours. They called it the heartbeat of the object. Now we know that heartbeat was caused by rotation. For the first time ever, we have a confirmed rotation measurement of an interstellar visitor from directly watching the jets wobble. So, where are these jets actually located on 3I Atlas? The December images show two jets on opposite sides, one toward the Sun and one away. Both stay tightly focused across hundreds of thousands of miles. The best explanation is that these jets are shooting out from near the north and south poles of the spinning object. Think of a spinning top. The poles barely move while the middle spins fast. If you put jets at the poles, they wobble slightly as the object rotates but stay pointed in mostly the same direction. As it spins, the polar jets wobble by about 7 degrees. This organized pattern tells us 3I Atlas is not chaotically tumbling or fragmenting. This is stable rotation with jets locked to specific spots. This discovery is a huge deal. The first interstellar visitor discovered in 2017 showed no jets at all, just a bare object tumbling. Borisov, the second visitor in 2019, had a tail but no organized jets or measured wobbling. 3I Atlas is the first interstellar object where we can actually watch the jets wobble and calculate exactly how fast it is spinning. That 15.5-hour period is a direct measurement. This matters because rotation tells us about internal structure. The fact that it maintains stable rotation means it is not a loose pile of rubble. It has enough structural integrity to spin smoothly. It shows that interstellar objects can maintain organized structure for billions of years. Now let's talk about the sunward jet itself, because the scale is insane. The jet pointing toward the sun stretches at least 400,000 kilometers, roughly the distance from Earth to the Moon, and some measurements suggest it might reach 1 million kilometers. But here is what makes it truly bizarre. This jet is staying focused like a laser beam with an opening angle of only 6 to 8 degrees. It is more than 10 times longer than it is wide. Normal comet tails spread out and get fuzzy, but this jet is maintaining a tight beam across distances where it should have turned into a huge scattered cloud. Why does it stay so focused? Scientists figured out it has to do with the size of the dust particles. Usually, comet dust is about half a micron, but the particles in 3I Atlas jets are between 1 and 100 microns. A human hair is about 70 microns wide, so these range from much smaller than a hair to a bit bigger. These particles are 1,000 to 1 million times heavier than normal comet dust. Because they are heavy and slow, moving at only about 5 ms, they travel toward the sun for days before solar radiation pressure finally stops them and pushes them back. That slow, steady movement creates the tight-focused beam we see. The two jets also tell us about what happened when 3I Atlas passed close to the sun. In October, the sun's gravity bent the object's path by 16 degrees like a slingshot. Despite this, the sunward jet stayed pointing toward the sun. So why do we see two jets now? The answer is heat. During the closest approach, one side got blasted with solar energy. That heat didn't just stay on the surface. It slowly conducted through the object to the other side. As that heat reached the opposite side, it warmed up ice that was in shadow, creating a second jet on the opposite pole. 3I Atlas has internal heat conduction happening, activating regions not even facing the sun. Most astronomers say this is natural comet behavior with unusual features. The James Webb Space Telescope measured the chemistry and found typical molecules like carbon dioxide and water. The carbon dioxide to water ratio is extremely high at about 8:1, which scientists explain as the result of billions of years of exposure to cosmic rays. 3I Atlas is estimated to be 9 to 13 billion years old, formed long before our sun existed. High-energy particles hit the surface and changed the chemistry over aeons. The switching brightness pattern proves the object is stable. The 15.5-hour rotation period is real and measurable. The double jet structure tells us the object has internal structure allowing heat to move from one side to the other. Most comets lose their unusual features after passing the sun, but 3I Atlas maintained its organized structure. Whether it's an ancient comet or something else, the Hubble images have given us the first direct rotation measurement of an interstellar visitor. What happens next? The International Asteroid Warning Network is running a campaign right now through January 27th. Telescopes worldwide are measuring jet velocities and mass loss. Once that data comes out, we will have a complete picture of 3I Atlas. But the big event is March 16, 2026, when it makes its closest approach to Jupiter. The object will pass at about 53 million miles, almost exactly at Jupiter's Hill radius, the gravitational sweet spot. Scientists are preparing every major telescope to watch that flyby. They will look for course changes, see if anything separates from the main body, or if new objects appear in orbit around Jupiter. These Hubble images have changed the game, providing a landmark case for understanding interstellar visitors. In just 3 months, when 3I Atlas reaches Jupiter, we are going to learn a whole lot more. If you watched to the end, please click the like button and let me know your thoughts. God bless you.